we are going to discuss about the torsion. So the torsion mean the twisted deformation developed in shaft due to the application of torque called the torsion. In the mechanical engineering industry, there's a lot of application regarding to the torsion. In a vehicle suspension system also use the torsion bar, and also the power transmission, there's a lot of application. In a mechanical power transmission, the shaft subjected to a torque, that means shaft subjected to a torsion, that means the twisted deformations. Then if, for example, if you take the motor, when giving output, mechanical power output from the motor shaft is subject to a torsion. When giving the output from a turbine, the turbine shaft is subject to a torsion. When giving a power input to the generator, through the shaft, it is subjected to a torsion. There's a lot of application relating to the torsion. If you are going to work as an engineer on a industry, you will definitely find the application regarding to the torsion. So this topic is very, very important. Under this course, under this topic, we are going to discuss how to design a shaft for a certain torque application. How to design a shaft, how to select a material, how to design a diameter, what is the deformation for certain torque. We are going to analyze under, we are going to discuss under this topic. So this topic is very, very important. Okay, let's move to the theory related to the torsion analysis. Okay, let's move to the theory of the torsion analysis. Theory of torsion analysis. The torsion, earlier I defined this torsion. The torsion mean twisted deformation. Twisted in shaft due to application of torque is called torsion. Twisted deformation developed in shaft due to application of torque is called torsion. So what is meant by the twisted deformation? What is meant by the twisted deformation? The twisted deformation means, let's take a shaft. Let's take a shaft. The one end is fixed support. From the front end, this kind of torque is applied. This kind of torque is applied. Before applying the torque, let's consider the line on the surface of the shaft as this. Then what happens? Due to application of this torque, this end rotates with respect to the fixed end. This is called twisted deformation. This is called twisted deformation. Let's take this point as A. Due to the twisted deformation, now it moves to the A dash position. Now it moves to the A dash position. I will draw the radial line to A. Let's consider the radius O and A dash. The angle between these two, listed as theta, is called twisted angle. Twisted angle. Okay, twisted angle. Then this. So what do you think? This theta is directly proportional to the torque. what happens when the torque increases, theta also increases. Torque increases, theta also increases. There's a direct proportional relationship between the theta and torque. Later we are obtaining the equation relating these two parameters. Okay. Then let's see, if we draw the free body diagram for the above application, free body diagram, that means I'm going to separate this shaft and I'm going to consider what are the all the forces and torque apply on this shaft. Then you can see this is the applied torque. From the fixed end, the reaction torque is given. This is called the reaction torque. This is called the applied torque. Due to this applied torque, reaction torque is given. You can see this is the end we are applying the torque. You can see this torque is transmitted to this end. How this torque is transmitted from this end to this end? The torque, here you can see the torque has transmitted to from this end to this end. Okay. This torque is transmitted from this end to this end due to development of internal torque. Due to development of internal torque. So what is meant by the internal torque? This is applied torque. This is the reaction torque due to fixed support. Then what is the internal torque? If we section intermediate position, somewhere in this kind of position, we consider the cross-sectional plane. Here the cross-sectional plane on the x-axis. On the x-axis. On this cross-sectional plane, the torque is developed due to externally applied T torque. This torque also T. Okay. Due to development of this internal torque, each and every cross section, this applied torque is transmitted to other end due to development of internal torque. Okay. Then if we consider the two section, let's take, we are going to consider the two different sections. Let's take A part and the B part. I will draw this A part and B part separately. I will draw the A part and the B part separately. Okay, I will draw the front view. This is the A part. I will draw the other part, the B part. This is the applied torque. This is the internally developed torque. Internally developed torque in other way. This is the torque developed in this cross section. Then this is the torque developed at this end on the B part. Okay, then this, if this is torque T, this one also should be T. This one also should be T. Considering the equilibrium of this separated part. These are called internal torque. These are externally developed torque. This is the reaction torque. This is the action torque. Action torque, internal torque, reaction torque. This internal torque developed due to action torque. Okay. Then let's see how to develop this internal torque. How this, if you take a certain cross section, how this internal torque is developed. How internal torque is developed. Internal torque is developed. How internal torque is developed. The internal torque is developed due to shear stress. Due to development of shear stress. due to development of shear stress. This internal torque is due. So what is mean by the shear stress? Shear stress. You already know this shear stress. I will just refresh your memories about this shear stress. I will just refresh your memories about the shear stress. So what is mean by the shear stress? So then what is mean by the normal stress? What is mean by the normal stress? What is mean by the normal stress and the shear stress? Normal stress, the stresses which are acting normal to the plane called the normal stresses. The shear stress, the stresses acting on a plane parallel to the plane called shear stresses. For example, let's take this kind of object subjected to this kind of force, inclined force. This is the force acting on this plane. Let's consider this surface area as A. The inclined direction to the horizontal theta. We can resolve this force into a two component parallel to the plane, that means along the plane if cos theta, the perpendicular to the plane if sin theta. Okay. If we consider the normal stress acting on this plane, normal stress acting on, what is the normal symbol used for the normal stress? Sigma. If sin theta divided by A. This is called the normal stress acting on this plane due to the F force. At the same time, we can write the shear stress. The tau is equal F cos theta divided by A. So we are using the symbol tau for the shear stress. Tau for the shear stress. This is called the shear stress component. Shear stress component. The shear stresses, the stress acting parallel to the plane on the plane is called shear stresses. Okay. I think you know these two, the difference between these two. Yeah. Then again the shear strain. What is the shear strain? Shear strain. So what is the symbol used for the shear strain? Yeah. What is by the shear strain? You know the normal strain, epsilon, you know. The shear strain. The shear strain we are defining in this way. Let's take this kind of object. This end is fixed. The shear force is acting on the top plane. Shear force is acting on the top plane. Okay, then due to this shear force, this material is top plane is shifted in this way, like this. It is deformed, forming this kind of shape. Then amount of shift, let's take it as the delta x, the amount of shift of this top plane, delta x. Then this is the reference plane we are considering, it is fixed. Then distance between these two planes called L. The shear strain we are defining, in this way is equal delta x divided by L. Delta x divided by L called shear strain. Actually, it is approximately equal. You can see the this is a right angle triangle. If you take the let's take this angle as gamma. Tan gamma is equal delta x divided by L. Tan gamma is equal delta x divided by L. Tan gamma is equal delta x divided by L. In here, the tan gamma is equal delta x divided by L. Here, what is mean by this tan gamma? 3. here in real situation this gamma is a very small angle. In real situation the gamma is a very small angle relating to this dimensions of the object L, relating to L. So then you know the tan gamma is equal its angle value in radians for small angles. Tan for small angle of tan, its angle value in radians equal to the tan value of the angle. So we can write this equation: gamma is equal delta x divided by L. This is called the shear strain. Okay, this is called the gamma is called shear strain. 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 Okay, then this is the, as a note, I refresh your memories about the shear stress and shear strain. This knowledge is important when you are going to derive the torsion equation later. Okay, then how, let's see how the shear stress develop on these shaft cross sections. How shear stress develop on these shaft cross sections. Yeah. Okay, let's take the shaft. Let's take the previous example. Okay, let's take the previous example. So I am going to consider the two the internal sections. Now let's consider the shaft, the then due to the application of torque, the shaft rotate this end rotate with respect to this end. So I am going to take this one as the reference plane. This is the reference plane. Okay, this is the reference one. This I am assuming, I am considering the rotation of this plane with respect to this plane. So this plane rotation I am going to equate to 0. So then due to the application of torque on this shaft, it is rotating this way. So I am going to consider the intermediate plane. Yeah. Okay, let's take this kind of section. I will draw that one also. This is the internal plane. This is the reference plane we are considering. Then due to the internal torque, this is the externally applied torque, this is the internal torque, Then let's take the shaft length as L. The before applying the torque, let's take the line drawn on the surface of the shaft as in this blue color one. Then after applying the torque, it is subject to twisted deformation. That means with respect to this and this in this rotate, let's take this rotation as in this way. Let's take the radial lines. Then this angle called theta, twisted angle. This angle is called twisted angle. That means A position to A dash position, this plane is surface is rotating. Okay, then I'm asking the question, if we consider the surface area of this kind of position, what is the shear strain related to this surface area? It is in r distance away from the radius. What is the shear strain related to this material area? Shear strain related to this material area. So let's move to the definition of the shear strain. Shear strain, the amount of shift of the plane divided by the distance between the reference plane and the considering plane. Okay, here what is the reference plane? This one. This is the considering plane. Length is L. What is the amount of shift? What is this length? This length is equal to r theta. Then the shear strain, the gamma is equal r theta divided by L. R theta divided by L. That means the shear strain at this edge. Shear strain at this edge. I will draw the front elevation. We are looking from this direction. Shear strain related to this kind of area. Shear strain related to this kind of area. Then if you take the shear strain relating to the r distance away from the r is the variable, r distance away from the radius, how we can write? The gamma is equal r theta divided by r is the variable. R is the variable. Okay, r is the variable. Then we can relate this shear strain. This equation, no? Sigma is equal E into epsilon. This is how we are relating normal stress to normal strain. Then same as we have in the equation relating the shear stress and the shear strain, G and gamma. The G is called modulus of rigidity. Modulus of rigidity. G is a material property, same as like elastic modulus of the material. Elastic modulus is also a material property. The G also material property. It's depend on the material. Then we can develop shear stress and the shear strain if you know the material property G, modulus of rigidity. The modulus of rigidity. Okay, then I'm going to write the equation. I'm going to find the shear stress tau at this position. Tau is equal from this equation G r theta divided by L. R theta divided by L. So I'm going to write this equation as equation 1. So then I will represent this stress also. I'm going to represent this stress also from r distance. If you take the certain dA surface area, the stresses acting on this surface area is tangent tau, like this. Okay. Then tell me, due to this shear stress, what is the force acting on this dA surface area? dF force is equal shear stress into dA. Shear stress into dA. So if you want to find the dF force, so then the dt, the torque around this O point due to the dF force is equal dF into R, the force into lever arm. The dt we can write including this equation. dF, I will write this one, G r theta divided by L into R. Okay, into R into dF, the tau or dA. Yes. Then you can see this equation. If you want to find the total torque, what we have to do, we have to integral. Okay, T G r square theta divided by L dA, integral all over the surface area. That means the torque developed on this cross section, total cross section, is equal. Here you can see the theta is a constant, L, the length of the shaft, also a constant. Theta is a constant for a certain torque application. The torque is constant, the theta also constant. So we can take it out from the integral sign, these terms, g theta divided by L. G theta divided by L, we can take it out from the integral sign, a r square dA. Okay, you know this term, no? You know this term. What is this term? It's a called polar second moment of area. Polar second moment of area. It's a cross-sectional property. It's a cross-sectional property, like product moment of inertia, second moment of area. Okay, it's a cross-sectional property. You know this equation, the J. So that I will write the J, put in this equation, that T is equal g theta divided by L into J. I am going to rearrange this equation. T over J is equal g theta divided by L. So I will write this equation as equation A. I will write this equation as equation A. Okay. Then previously, from the equation 1, I am going to take the equation 1 in here. From equation 1, what is the equation 1? Tau is equal, the equation 1, g r theta divided by L. I am going to rearrange this equation. Tau over r is equal g theta divided by L. Let's take this equation as equation B. So I am going to combine these two equations, A and B. I am going to combine these two equations, A and B. So how to combine? T over J is equal g theta divided by L is equal tau over r. This is called torsion formula. This is called torsion equation. This is called the torsion formula. This is the equation we are going to use to analyze the torsion developed in shaft when it is subject to a torque. So in this equation you can see r is the variable. R is the variable. Here the torque mean the torque developed in the internal cross sections, J cross sectional polar second moment of area, G modulus of rigidity, theta angle of twist, N L length of the shaft, tau mean the shear stress developed, R mean the distance from the radius. Here you can see, let's take this equation, tau. Tau is equal g theta divided by L. I'm going to use this equation. T over R is equal g theta divided by L. For certain torque application, g is a constant, theta also a constant, L also a constant, because L length of the shaft constant, the modulus material property is a constant, theta is a constant for a certain torque. Okay, so then if we take the tau is equal g theta divided by L into R. Okay, so then we can represent, if we take the circular cross section, we can represent the graphically, we can represent the shear stress developed in this way. So what is the shear stress at the 0? R is equal to 0, that shear stress is equal to 0. This is a y, it's like a y is equal mx type, no? Y is equal mx type. So it is maximized at this edge. R is equal to R, capital R. It's having the linear relationship like this. It's having linear relationship like this. Okay. It is maximized at this edge and the 0 at the. So what it means? It means if shaft going to fail due to the exceeding the torque apply on it, the initial crack develop on the surface of the shaft, not from the internal, because the shear stress is maximized at the surface of the shaft. That is the reason. Okay? The initial crack develop on the shaft. Okay, then if you take the hollow shaft, the same diagram we can draw in this way. If we take the hollow shaft, same diagram we can represent in this way. Here the internal, at the internal radius there is a value, certain value. At the edge it is maximized. It is like this. For the internal, that means at the internal surface also subjected to a certain stress, shear stress. At this edge also there is a stress is maximized. The tau is maximized. Tau maximum. Here the tau maximum value. Tau maximum value. Okay. Now you know we have obtained the torsion formula. So I will obtain this equation also for the J also. Let's see the polar second moment of area. Polar second moment of area. For the circular cross section, let's see how to find the polar second moment of area. Okay. For circular cross section, how to find the polar second moment of area. So I am going to consider the dA surface area. This is the dA surface area we are considering, dA. Then definition, what is the definition for the J? J is equal R square dA integral all over the surface area. This is the definition for the J, polar second moment of area. Then here this is the dA surface area. I am going to select. From a R distance from the radius. Okay. Then how to cover this entire surface area? If we change the theta from 0 to 2,5, we can cover ring shape surface area. Then if we can move this from 0 to R, we can cover the entire surface area. That means we have to use the double integral to cover entire surface area of this equation. Then the double integral R square, the dA we can write in this way, theta d theta. Theta I am going to measure from this y-axis. This is the theta. R d theta into dr. That means the dA surface area is equal, R d theta into dr. Okay, I think you will clear with this one, no? This is the surface area we are considering, very small surface area, dA surface area. This length is equal dr. This dimension is equal R d theta. That's why we are taken this way. Okay, then theta, how we can vary the theta to cover entire surface area? 0 to 2,5. R, how we can vary R 0 to, let's take the internal diameter as capital D, d by 2. So then J is equal the 0 to d by 2, then R is square, we can take it out from the R into cube, no? R into cube, then integral d theta into dr 0 to 25. So then R into cube theta 0 to 25 dr integral 0 to d by 2 j. Okay, then the j is equal, here the, what is the value for that, is 25, no? 25, I am going to take it out from the integral sign, 0 to d by 2 r into cube dr. So r into 4 divided by 4, 0 to d by 2 into 25 is equal j. Okay, this is the, what is this, number 6. Then if we can simplify this equation, 5 over 2 d by 2 over 4 g is equal. Here what is the value? The 2 4 8 16, here the 32, 5 d4 over 32. This is the equation for the polar circumference of area for the circular cross section. Okay, circular cross section. Then what happened for the hollow cross section? Okay, for the hollow cross section, let's take internal diameter as simple d, the external diameter as capital T. In this situation, the R we have to calculate, the J we have to calculate same definition, under same definition, AR square dA, what we took early. So the same equation here, J is equal 0 to d by 2, sorry, I'll show you that 25 r square r into cube d theta dr. In here the r we have to vary from, here this variable r we have to vary from not 0, simple d by 2 to capital D by 2. This is the only difference when taking the hollow shaft. Okay, when taking the hollow shaft. So that after simplifying this equation, we will get this equation, the 5 d4 over d4 minus simple d4 over 32 is the equation for the hollow circular cross section J. Okay, this is the theory related to the torsion. There's another topic we have to discuss. Okay, let me summarize what we discussed so far. Okay, torsion analysis topic we started. Then we defined the torsion. The twisted deformation developing shaft due to the application of torque is called torsion. There's a relationship between the torque and the angle of twist. Then due to the external applied torque, the internal torques are developed. Then how internal torque is developed? Because of the development of shear stress. So I will just refresh your memories about the shear stress and the shear strain. Then the shear strain. Yeah, then we consider what is the shear strain developed in shaft when it is subject to a twisting. So then we have obtained the equations for the shear strain. If you know the shear strain, by multiplying it by the modulus of rigidity of the material, then we can get the shear stress. Then if we represent this shear stress on this circular cross section in this way, is tangent to the radial line. Then if you consider the force dF, force small force acting on a dA small area, dF is equal to tau into dA. If we integral, we can find the total. If you multiply it by the lever arm in the R, we are getting the torque due to the shear stress acting on this small surface area. So then to calculate the total torque, we have to integral all of the surface area, then we are getting these equations. Okay, by rearranging this equation, we are getting A. Then by rearranging the first equation and by combining with this A equation, we are getting the torsion formula. This is the torsion formula. Okay, torsion formula. In this torsion formula, J, you have to define this one, the torsion, how the shear stress vary in a radial direction for the solid circular shaft cross section, the hollow circular shaft cross section. Then we obtain the equation for the Fowler's second amount of area for the hollow solid circular shaft. Then we obtain Fowler's second amount of area for the hollow circular shaft. Okay. Then another small theory part under this subject, power transmission through the shaft. Power transmission through the shaft. Power transmission through the shaft. There's a lot of industrial application. The shaft are used to transmit the power. Okay. For example, let's take one of the example. Let's take this is the motor. Let's take this is the motor. Then it is this is the motor shaft, then the motor coupling, then the output shaft. Then let's take another bearing also. Then let's take at this end the axial fan is connected. Okay, power transmission to the shaft. Here you can see the motor is connected to the shaft coupling, and axial fan is connected. Then let's take, due to the air flow, due to the air friction, the resistive torque apply on the shaft. If you look from this direction, you can see it is connected to the shaft. I will do the shaft. This is the resistive torque apply on the shaft from the air. Resistive torque, resistive force. Okay. So in this, then the motor produces torque to rotate against this air friction. Okay, motor produces torque against this air friction. Torque E also T. Then this is the air friction. This is the produced torque by the motor. Okay. Then if it is not accelerating, the shaft are not accelerating, these two are equal. Okay, these two are equal. Okay, if you consider the bearing frictions and everything is 0, these two are equal. Other than this, if there's a bearing friction and other friction in this motor and the bearings, this shaft is greater than this value. Okay. Anyhow, we are going to discuss. You can see that electrical power is converted by the mechanical energy, then it is transmitted through the shaft from this end to this end. This is the application. The shaft are used to transmit the torque. One of the application. Same as in a turbine shaft, when turbine rotate, then the power is transmitted to the generator through the shaft. Okay. The engine producer in a ship engine produces kinetic energy by combustion of the chemicals, fuel, then it transmitted to the propeller through the shaft, propeller shaft. So that means these are the application of power transmission through the shaft. Okay, before going to the obtain the equation, first tell me what is meant by the work. In simple way, work is equal the force into distance travel, no? Force into distance travel. Okay, force into distance. Then the power, what is meant the power? The work done per second, work done per second, the work done here, the time taken for a certain work, then the work done per second is called the power. Okay, so then the P is equal F is divided by T. F is divided by T. Okay. Then in this application, I'm going to write the air friction. This is the torque due to the air friction as T on the shaft. Okay. Then this T torque we can represent by a force and a lever. Force and a lever. This is the F. This is the shaft R. Okay. Then the T is equal F into R. Okay. That means this is these are equivalent to this one. The instead of that means what I did, I represent this torque by a force and a lever. The same, no? Same. Then now we can easily find this equation. When rotating one revolution, what is the work done against the air friction? For one revolution, work done against the air friction. What is the work done? When revolution, one complete revolution means this force travel on a circumference distance and it comes to this position. What is the distance traveled by the force? 25 R. Then applied force F. This is the work done per one revolution. Okay, work done per one revolution. Let's take this shaft is producing n number of revolutions per second. N revolutions per second. So what is the work done per second? Is equal 25 in R F. 25 in R F. Okay. So what is the work done per second? Power, no? Power transmitted. Power transmitted to the shaft is equal to 25 in, for the instead of RF I'm going to put the T. That means the P is equal to 25 in T. 25 in T. Here N mean revolutions per second. N. The T mean the torque apply on the shaft, torque develop in the shaft. Okay, this is the power transmitter. That means the torque this shaft is subjected. T, the N, number of revolutions per second. This is the power transmitted to the shaft. This is the power transmitted to the shaft from this end to this end. Okay. Then this equation we can rearrange in this way also. The P, the 25N. What is the 25? What is the 25N? The 25N. The 25N mean omega. Omega is equal to 25N. Here the omega mean angular velocity. Radians per second. Radius per second. That means the 25N mean it's N mean the revolutions per second. The 25 radian value for the one circular. The 25N mean per second radian value. The same equation we can write in this way also. Here the omega mean omega, we have to measure radians per second. The torque, if we put the torque in Newton meter, we are getting the P in watt. P in watt. Okay. This is all over about the theory under this torsion topic. Under this torsion topic. So next we are going to do some example related to these theories, how to design a shaft, how to select a material, then how the shaft are deforming different torque applications. We are going to discuss in the example questions.